This is example 24, number 24, using power series to solve this differential equation, which is y prime plus x cubed y is equal 0. So let us use this power series to solve this. Means our solution is in this form here. Then we have to take the derivative of y up to the order that we have. Y prime is equal n, sigma n is equal 1 to infinity. So again, starting from 1, because when n is equal 0, this term is 0. So n is equal 1 to infinity of n cn x n minus 1. So we plug in this y and y prime into the differential equation. So here y prime with its term and y with its term in series. And then since here, and like the example, we have a number, so a constant multiple is okay, but since here I have the variable, I have to put it inside, put in that xn times x to the power of 3, the same base. That means we add the exponents, so x to the power of n plus 3. And now our objective is to have the same power, so we have to do some substitutions. Whatever we have here, n minus 1, this power we put it k is equal n minus 1, and now this power n plus 3 is k is equal n plus 3. So we will see while doing the substitution, this series will be in terms of k, this series will be in terms of k, and then we have x to the power of k in both series. Therefore we have, when n is equal 1, that means substitute here n is equal 1, we get k is equal 0, so it starts from 0, and then n is equal k plus 1, so k plus 1 for n, and here n minus 1 is your k. Then here similarly, when n is equal 0, substitute here 0, then k is equal 3. So start from k is equal 3, and wherever I have n, I put k minus 3, n is equal k minus 3, so I have x to the power of k. So in both terms, I have x to the power of k, but combine this series as one sum notation, we have to start from the same index. Therefore, to start this one from k is equal 3, we go over the first three terms. When k is equal 0, k equal 1, k is equal 2, what is this term? So when k is equal 0, substitute here, k is equal 0, you get 1 times c1, k x to the power of 0, which is 1. Okay, remember, x is different than 0. So c1 plus 2 times, when k is equal 1, 2. So 2 times c2, k is equal 1, c2, x to the power of 1, which is x. Now when k is equal 2, we keep going until we stop one term before, such that I can start with k is equal 3. So k is equal 2, I substitute again when k is equal 2, I get this term, plus now k is equal, sigma k is equal 3. So this whole thing, all these terms here with this sigma is corresponding to this, starting from k with this notation, sigma k is equal 3. And now we have this over here. Now we have these two sigmas starting from the same index, k is equal 3. Then I can combine them, and I have x to the power of k as a factor. So as a factor of what? K plus 1 times ck plus 1 from this term, and ck minus plus ck minus 3 from the other term. And we have this c1, don't forget these terms. So this series is equal 0 while x is different than 0. Therefore, if every constant coefficient over here should be 0. So c1 is 0, c2 is 0, c3 is 0, and this constant multiple here should be 0. Remember, from k is equal 3 to infinity. What we got is c1 is equal c2 is equal c3 is equal 0, and ck plus 1, we solve for it, the updated one, remember, is equal minus ck minus 3 over k plus 1, for k is equal 3, 4, and so on. So k is equal 3, starting from k is equal 3, we substitute over here, 3 plus 1, which is 4, and then 3 minus 3, which is 0, so I get minus c0 over 4. Then when k is equal 4, see here, notice that I have 1, 2, 3. 3 consecutive constants is 0. When I substitute for k is equal 4, I get C5, I get, in terms of C1, C1 is 0, so it's 0. So the next 3 terms, which means these 2 terms here, will be 0. K is equal 5, I get C6 is equal 0, k is equal 6, C7 is equal 0. Now when k is equal 7, I get C8. So C8, pay attention here, k plus 1, C8. So k is equal 7, 7 minus 3, which is 4, so minus C4 over 7 plus 1, which is 8. So which is minus 1 over 8 times C4. What is C4? Is minus C0 over 4. So this is C0 over 32. Now remember, if k is equal 8, I have the 3 next consecutive will be 0. Such that, we know this, notice this, such that we don't do so many calculations. We can have the next term, which is when k is equal 11, we get C12. C12 in terms of C8 and C8 in terms of C0. So we have all these coefficients here will be in terms of C0. Remember our power series in expanded form, then we have C0, which is here. This one for x, C1 is 0, C2 is 0, C3 is 0. Now next, C4, x to the power 4. So I put x to the power 4 and I look for where is C4. C4 is here, minus C0 over 4. So I put minus C0 over 4. Plus, I put next term is x5, C5, x5, 0. C5 is 0, C6 is 0, C7 is 0. So I have C8. C8 is the coefficient of x8. So x to the power of 8 times C8, which is C0 over 32, plus, keep going until I have the K12 at C12, which is different than 0, times x to the power of 12. C12 is minus C0 over 12 times 32. Leave it as a product like this. So it's minus C0 over 12 times 32. So you notice I have a first order differential equation, meaning I have one constant as a factor of y1. This is my y1 as a power series. So C0 times, don't forget this term here, 1 minus 1 over 4 x to the power 4 plus 1 over 32 x to the power of 8 minus 1 over 12 times 32 x of 12 plus and so on. So this is our solution in terms of the power series. In terms of our power series, so this is C0 and this is your y1. Okay, so I have this y1, which is fifth parameter in its power series. Actually, this is an exponential form of the solution, so we can just leave our solution like this.